wondered how it would be great to know things in advance, like knowing the jackpot combination of numbers in a lottery, or simply knowing what will happen next in a few hours, days, or weeks, because I've also thought of those things. You know, it would be really great to know what will happen in the future, but unfortunately, you really can't do that because nothing is certain in life. However, our friend here, I used to work, by the way, he's an award-winning mathematician, revealed over the course of history, mathematics has the tools we need to better manage the uncertainty that pervades our lives. So let's dig deeper.
In the 8th chapter of Ian Stewart's book Nature's Numbers, he challenged Newton's vision and Laplace's idea of determinism. Sir Isaac Newton's intellectual legacy was a vision of a clockwork universe. It is an image of the universe as a mechanical clock. It continues ticking along as a perfect machine, with its gears governed by the laws of physics, making every aspect of the machine predictable. Marquis Pierre-Simon de Laplace's idea of determinism is the belief that the past completely determines the future. He also once stated that we may regard the present state of the universe as the effect of its past and the cause of its future. These concepts produce an image of a totally deterministic world, one leaving no room for the operation of chance. Contrarily, many encounters in our daily lives are purely occurring by chance or lady luck,
such as bumping into an old friend at the mall or discovering an old bookmark inside a book from the library, or finding a lost wallet along the way. By this, it seems more likely a universe where dice play God.
Now, is our world truly deterministic as Laplace claimed? Or is it governed by chance as it often seems to be? And if he is right, why does so much of our experiences indicate that he is wrong? One of the most exciting new areas of mathematics is the chaos theory. Is it really exciting? We'll see. This theory claims to have many answers to the questions earlier. Whether it does or not, it is certainly creating a revolution in the way we think about order and disorder, law and chance, predictability and randomness. According to modern physics, nature is ruled by chance on its smallest scales of space and time. There are at least two contexts in which to discuss these, and you need to know. Let's go!
Hi, let's continue. On with the two contexts, quantum mechanics and classical mechanics. Let me first explain what is quantum mechanics. Quantum mechanics is a physical science that deals with the behavior of matter and energy on the scales of atoms and subatomic particles or waves. It's the motion and interaction of individual objects of bigger collection. Quantum mechanics is the view thus from Einstein's famous statement, "You believe in a God who plays dice, and I in complete law and order." However, there have been increasing many physicists finds that there is something questionable in the orthodox physical view of quantum indeterminacy, and something that is missing from conventional quantum mechanics might be the hidden variables. If quantum mechanics is correct about indeterminacy, then the universe follows the deterministic laws, which results from an effect called decoherence. Decoherence causes enough quantum systems to lose almost all of their indeterminacy and behave more like classical mechanics. Classical mechanics is studying movement with Newton's laws. Classical mechanics deals with the motion of bodies under the influence of forces, or with the equilibrium of bodies when all forces are balanced. This reinstates classical mechanics for most human-scale purposes. Actually, Horses, the weather, and Einstein's celebrated dice are not unpredictable because of quantum mechanics. However, they are unpredictable in classical mechanics because of the hidden variables. Perhaps it's not been so surprising when it comes to horses, as living creatures have their own hidden variables, such as what kind of hay they have eaten for their breakfast. But it has been a surprise for those meteorologists who have been developing massive computer simulation of weather in the hopes of predicting it for months ahead. And it was rather startling when it comes to dice, as it was one of our favorite symbols to use for chance. Dice are just cubes, as it is just a tumbling cube should be no less predictable than orbiting planets. As both objects obey the same laws of mechanical motion, they are both in different shapes but equally regular and mathematical ones. To see how unpredictability can be reconciled with determinism, think about a much less ambitious system than the universe, namely, drops of water dripping from the top.
Okay, so in the year 1978, a bunch of iconoclastic young graduate students at the University of California at Santa Cruz formed the Dynamical Systems Collective. When they began thinking about the water drop system, they realized that it's not as random as it appears to be. They recorded the dripping noises with a microphone and analyzed the sequence of intervals between each drop and the next drop. What they have found was short-term predictability. For example, if I tell you the timing of the 3 successive drops, then you will know when the next drop will fall. The point is that we can never measure the initial state of a system exactly. The most precise measurements yet made in any physical system are correct to 10 or 12 decimal places. But Laplace's statement is correct only if we can make measurements to infinite precision, infinitely many decimal places. And of course, there's no way to do that. Nothing short of total perfection of measurement will do. This phenomenon is called sensitivity to initial conditions, or more informally, the butterfly effect.
Hi, so what is the butterfly effect? Butterfly effect is not the phenomenon we encounter when our crush texts us. You know what I mean, right? No, that's not it. The butterfly effect is the idea that small, seemingly trivial events that may ultimately result in something with much larger consequences. Tiny changes on initial conditions have big effects. The term butterfly effect comes from an analogy where a butterfly flaps its wings in Tokyo and then a tornado occurs in Tennessee. The butterfly effect is intimately associated with high degree of irregularity of behavior. All the butterfly effect does is to make the system follow on different paths on the same attractors. We used to assume that simple causes must produce simple effects, implying that complex effects must produce complex causes. But now, we know that simple causes can produce complex effects. But sensitivity to initial conditions renders behavior unpredictable, hence irregular. For this reason, a system that displays sensitivity to initial conditions is said to be chaotic.
Chaos. Chaotic behavior obeyed the deterministic law, but it is so irregular that to the untrained eyes it looks pretty much random. Chaos is embedded in nature and reality, whether it is unseen or unrealized by many. It's create a revolutionary in a way that we think of order and disorder, law and chance, predictability, and randomness. Within the apparent irregularities, randomness, and disorder in occurring events, there are actually underlying pattern, interconnectedness, and deterministic law that can highly sensitive to the initial condition. Small differences such as an error in miscalculation can yield different highly affected outcomes. Chaotic behavior exists in the weather and climate, even in the stock market or traffic. As Edward Lawrence said, chaos is when the present determines the future, but the approximate present does not approximately determine the future. Base space. Base space is an imaginary mathematical space that represents all possible motion in a given dynamic system. It also states that when you put things into base space, everything will be calculated and can put into numbers. The base space is also a 3D place in which you plan a behavior in order to create a base portrait. Base portraits have shown the dynamic system tend to have a set shape which emerge in which system move forward, and these are called attractor. Attractor are also points that never repeat themselves and orbits never intersect. Lastly, the strange attractor is a type of chaotic dynamic system that can take up until indefinite number of different forms. Every chaotic process involves a kind of mathematical mixing in point-square imaginary base space. This is why sides are predictable but weathers not. Both involves the same kind of mathematics, but the dynamics of side does not get base space mixed up. Whereas of the weather does. It's not what you do, it's the way that you do it. Chaos is overturning our comfortable assumption about how world works, and it tells us the universe is far stranger than we think. Chaos is bound by rule. Creation of chaos is called the period of doubling cascade.
In 1975, physicist Mitchell Feigenbaum discovered a number that is associated with period doubling cascade. This number is roughly 4.669 and symbolized with the Greek letter delta. It became extraordinarily significant in both the mathematics and natural world along with pi. Feigenbaum's number tells us how the period of drifts relates to the rate of flow of the water and is a quantitative signature for any period doubling cascade. This very same number shows up in various experiments on liquid helium, pendulums, electronic circuits, magnets, and such. It is a new universal pattern in nature, one that we can see only to the eyes of chaos. A quantitative pattern, a number, emerges from a qualitative phenomenon. The Feigenbaum number has opened the door to a new mathematical world, one that we have only just begun to explore. Indeed, it is one of nature's numbers.
555.
Chardines!
And we're done!
That's it for our vlog about
Do Dice Play God?
Of Ian Stewart's book Nature's Numbers.